to the cloud. All right, so we have objective, pretty straightforward, learn how to use dot product and also its purpose. Dot product of vectors, u1, u2, u3, v1, v2, v3 is the sum of the product of the products of the components u1, v1 plus u2, v2 plus u3, v3. All right. I'm just saying that super quick because the definition, you know, it kind of is what it is. So in the act of demonstrating this skill, I think it'll become more more obvious what I'm after here. Looks like my Apple Pencil got disconnected. Let's see. I gotta plug it in. Hold on 1 second. Yeah, looks like maybe. Okay, we're up. All right. So yeah, a little demonstration goes a long way here. So when I want to find the dot of u and v, what I'm going to do is I'm going to take the corresponding components and multiply them together and then add those resulting values. All right, so my dot product is going to be 3 times -1 plus 5 times 3 plus 2 times 0. And we'll get into the meaning of it in a little bit. For now, we're just talking about the skill. All right, so 3 times -1, -3 plus 15 plus 0. Result is going to be equal to 12. All right. So again, that number has meaning, and we'll talk about its meaning, but for now, let's just focus on finding the dot products. All right, so same idea if it's an IJK form. I can rewrite IJ and K, sorry. I could rewrite IJK in component form. I tried to get cute with the highlighter here. It ends up looking kind of messy, but it's all right, I guess. You wouldn't have to show this step. You could skip it, but I just want people to see what the relationship is. All right, so those are my 2 component forms of the vector rather than the IJK notation. So when I want to find the dot of P and Q, I'm taking the 10, multiplying it by the -2. I'm taking the -4, multiplying it by the 1, and the 7 multiplying by the +6. So we're looking at -20 -4 plus 42. So is that 18? All right. So you see the term here, scalar product. That means the same thing. Right. Now, it only means the same thing because we're multiplying 2 vectors. We're finding the scalar product of 2 vectors. Otherwise, it would just normally be your ordinary distributive property, right? So scalar product is the dot product when applied to 2 vectors. All right. So then we see that we have some relationships that are familiar. The commutative property, the associative property, and the distributive property, all familiar stuff. Right? You're just reorganizing. That stuff should be pretty straightforward. The property of magnitude is the first interesting one. Right, well, they're all interesting, but that's the first one that's like, whoa, I didn't know that. All right, maybe you did. But the dot product between two vectors is the same as the magnitude squared, right? So if you think about it, it's really saying instead of finding the magnitude, which would be the sum of the squares of the components of the vector, under a radical, that's your magnitude, and then taking that result and squaring it, which just amounts to knocking off the radical, you could find the dot product of a vector and itself. That's pretty cool because that's an easier calculation. Now, in the end, it amounts to the same thing, but it's a little bit easier to do it, to carry out that process in your head, right? That's the benefit of this, well, one of the benefits of this relationship, right? So in number 3, we have the dot of A and B multiplied by C. Now it's the dot product of 3 vectors. Now we can follow the order of operations, take care of A dot B first. So I'll just kind of chuck that in here. I'm going to use this tool here. I'm just rewriting it for organizational purposes. Whatever you can do in your head, by all means, go for it. All right. Just remember, this is going to sound weird, but remember that 1 times 0 is not 1. Right? Just like above, 2 times 0 was not 2. Anything times 0 is 0. I only bring that up because that is, believe it or not, the most common error when it comes to dot product that I ever come across. And I'll tell you, there's at least 4 or 5 people per class that are good for that mistake on a test. Right? So just be careful. We're looking at 0 plus 4 plus negative 12. So we get a negative 8. More importantly, we gain from this the idea that a dot product can be negative, all right? Okay, so we'll file that away. So when we talk about what a dot product is and what it really means and what it tells us, then we'll start to kind of put all the pieces together. Now we're taking that result and we're dotting it against the C, but now this is a scalar value. This is a scalar multiple. So it's definitely simpler. And it gives us a result that's going to be a vector. All right. So we're looking at negative 40, comma 8, comma negative 24. Poor quality negative symbol. Negative 24. And so that's the final result. You have a vector that is, it's scaled up in absolute size by a value of 8, but it is going now in the opposite direction. All right, but that negative 8 comes from the dotting of A and B. All right. Now, number 4 is associative property. Well, it doesn't have to be. You could just carry out the operation if you want, double the C and then dot it. But the whole point behind this particular problem was to show you, to show you that you can regroup. So in the last one, I didn't really talk about it, but I did apply the commutative property, right? Because what I'd be looking at is negative 8. Oh, actually, I didn't have to, because negative 8 is automatically in the front. Forget what I just said. Right? But I suppose I could have, you know, if it were the other way around, if it were C multiplied by parentheses A dot B, then the commutative property would allow me to switch it and make it negative 8 times C. Didn't happen that way, but it could have. Here, what I want to do, just to apply a property and give you a sense of how it works, I'm going to reorganize and make it 2 parentheses, A dot C. So I'm dotting the A and the C, and then whatever I get as a result, I'll double that. All right. So it's going to make things a little bit easier. I'll use the highlighter this time. Highlighters or highlight tool. Okay, so it's looking at, I'm looking at 2 times 5 plus -2 plus -9, which is the same as 2 times -6, which is going to give me a -12. All right, so that's not too bad. You know, like I said, you could have changed it around. You could have, or you could, I'm sorry, I changed it around. You could have worked with it as it was. Double the C value, maybe right above the C, write 10, -2, 6, and then dot that against the A. Could have done that. Nothing wrong with that. All right, so it's just, I'm just giving you options. Really what I'm saying here. So here, for example, I'm dotting, you know, because this is the same as B dot B by rule. Right? So I didn't kind of invent this out of thin air. That's given right up here. Oh, why did that happen? Oh, I see. No, I don't see what. Oh, now I see. This rule, which is just telling me that I can take the dot product between 2 vectors and that'll give me the magnitude squared. Okay, so that's what I'm going to do. So I'm going to have B dot B, so that's 0, 2, 4, dotted against itself. And that's going to give me 0 plus 4 plus 16, which is going to give me 20. All right, so that's giving me a magnitude. That's a magnitude squared. So if I needed to, I would take the magnitude value, or I'm sorry, take this value, take its root, and I would end up with the magnitude itself. You know, let me just show you the proof real quick. It's pretty straightforward. So I'll just kind of chuck it. I'll just chuck it off on the side here. I got that little space right next to all the properties. So what I'll say is prove, and I'll take it as a typo. V dot V is equal to V squared in R3. Real number system 3. Right? Dimension 3, that is. Right? So what I'd be looking for, if it's in 3 dimensions, is V would be V1, V2, V3. Dotted against itself. When I take the dot product, again, I'm multiplying the corresponding parts and adding them together. So I'd be looking at V1 squared plus V2 squared plus V3 squared. All right, so V1 times V1, V1 squared. V2 times V2, V2 squared, and so on. All right, now what this is the square root of the magnitude of vector V. All right, This is, I'm sorry, it's not the square root. It's the magnitude actually squared. That is the definition, all right? But what I'll do is I'll just kind of chuck it in here because I don't like hocus pocus in my proofs. So what I'll say is V, the magnitude of V, and I'm going to use a triple equal sign here. Triple equal sign means equal by definition, which means that I'm pulling a definition from my knowledge bank, you know, my memory banks, right? Indicating that this step here is not a consequence of the previous step. It's something new that I'm adding. It's another given piece of information that I'm throwing in, all right? That's equal to V1 squared plus V2 squared plus V3 squared. All right, and so what that tells me is that V1 plus V2 plus V3 is equal to the magnitude of V squared. Which means that V dot V is equal to the magnitude of V squared. All right. The second to last step was actually a consequence of this step, right? By applying that relationship. Once I knew that the magnitude was equal to the square root, I'm like, oh, well, this is just that without the power of 2. I'm sorry, the power, the radical, which leads to the power of 2. All right. So that's a nice little, pretty straightforward, I would say, proof. You know, we've done ones that are a lot more complicated, derivations and proofs. So this is a lot nicer. All right. It won't always be this nice, but this is pretty not bad. All right. And since I always put a proof on a test, and in a lot of cases, those proofs are things that you could pull right out of your notes. Well, I know the one on the last test definitely was. You know, just if you take good notes, you already got one question in the bank. You know, so that's pretty solid. All right, moving along. We're going to talk about evaluating a dot product. We'll get into its uses, and then we'll kind of come back to the meaning of a dot product again. All right. So, so evaluating a dot product of the two vectors is the product of the magnitude of each vector and the cosine of the angle between them. All right. So that's a pretty strange one, right? Because you look at it and say, whoa, hold on a second, where did this cosine thing come from? And also, the dot product is the product between two vectors. That's pretty astonishing, right? But I'm going to show you where it came from, you know, because I'll get into the proof, and the proof is pretty awesome, right? So what we're looking at are two vectors, u and v, and the vector difference. All right. Now, one thing I do want to justify for you is where that difference is coming from, right? And I'm like, how do I know that last side is v minus u? That's a hell of a question. So first thing I'm going to do is think of that v minus u, because that came out of nowhere. That's like magic. Where is this guy making this stuff up from? You know? So this is the same as saying negative u plus v. All right. So what that tells me is that if I do the vector sum between negative u, so let me get a negative u. Here's u. Negative u would be that same vector just going in the opposite direction. All right, so I'll just plot that with a little negative u here. And then plus v. Well, vector sums being what they are, I prefer to go with the parallelogram is what I just said actually. Parallelogram approach. So if I want the vector sum, what I would need is to create a parallelogram between negative u and positive v. All right, so well, I could just take this and move it on down the line. I'm going to copy this bad boy. All right, so I have a nice looking parallelogram here. Now, if I connect to find the resultant, I'm connecting this point and this point. I'll put an arrow here, make it obvious, right? And I'll highlight the ones that I'm finding the sum between. I have the negative u and the v. This guy here would be my resultant, negative u plus v. Right now, in the process of creating the parallelogram, you know what I'll do is I'll shade it. I'll do like a nice light or like a neon green here. For those keeping score. So I created this parallelogram. In the process, I created another parallelogram, right? It's kind of interesting how that happens, you know, and I'll highlight that one. That's this parallelogram. All right. Now, I already had that one side in there, but even if I didn't, because opposite sides in a parallelogram are congruent, I would know that this side here, this guy right here, has to be the same length as this side over here. Let me actually thicken that up. And let me do it in this green color. No, green color is not going to work. Do it in purple. So these two line segments are congruent to one another. All right, so that's pretty nifty. I'm just kind of stuck with that negative and the tick mark kind of touching one another. We'll live with it. But those two opposite sides are congruent, so if one of them is negative u plus v, then so is the other. All right, so what that gets me is the idea that if one vector serves as a diagonal of a parallelogram, so you have one vector that's a side, one vector that's the other side, that's the diagonal, the remaining side would be the vector difference. All right, so you could always construct it out of that, and that's fun. That's good information. But what it gives us more than anything else is three sides of a triangle. Now, three sides of a triangle with an included angle, that gives us, or at least it leads us to the law of cosines. All right, because we can't assume a right angle. It's not simple SOHCAHTOA or Pythagorean theorem or anything like that. We'd have to apply the law of cosines, one variation of which is c squared is equal to a squared plus b squared minus 2ab cosine c. All right. The angle is the driving force behind the law of cosines. So wherever the angle is, that dictates all the relationships that follow. So in this case, what we would be doing is calling this angle C. Which would make this, sides opposite angles have the same name, just with a lowercase. So this would be side C in the law of cosines. So I know that I'm dealing with v minus u, because it's a little nicer to write it that way than it is to say negative u plus v. So v minus u. Now, v minus u is the difference between two vectors. All right, that's just a position, or that's just magnitude and direction. You know, if I want to square a number, that number needs to be a scalar. So what I would do instead is take the magnitude of v minus u and square it. The other two sides are going to be a and b. It doesn't matter which is which. So I'll call this one a and I'll call this one b, which makes this side a and this one side b. All right. It's commutative. It doesn't make a difference, so you can go either way with it. just so we have a little bit of consistency, I figured I would just name them so that we have it. So we're looking at v squared, but again, v is a vector. I'm squaring a vector. It goes back to that relationship. If I'm squaring a vector, that vector has magnitude and directions in component form. I'm really squaring its magnitude. I'm squaring the length of the side, which is the magnitude of v, plus the magnitude of u minus 2 times the magnitude of v times the magnitude of u. Doesn't matter what kind of multiplication symbol I use here because these are two scalars being multiplied. If you're familiar with the cross product, which we're going to get to tonight, you'll see that if you're multiplying vectors, it does matter what kind of multiplication you're using. But when you're multiplying scalars, it's just straight up good old-fashioned multiplication. And then cosine, so times cosine of my angle C, which is theta. So times cosine of theta. All right. So looking at the left-hand side, v minus u as a magnitude squared. I threw in there a little recall. You know, like usually when you see in notes or in a textbook, you see the word recall. It's like, it's usually something that you're supposed to recall from like years ago or like 2 units ago. It's not usually something that you're supposed to recall from 5 minutes ago, you know, like as in we just learned it. But I needed to designate it as something, right? So these are the rules that we're going to apply for this proof. These are the ones that are going to make sense, all right? So I know that v minus u as a magnitude squared is the same as v minus u dot v minus u, all right? So v minus u dot v minus u. The right-hand side I'm going to leave alone, right? Because that's already expanded out. If this thing is going to simplify, it's going to simplify because I cleaned up the left-hand side. The right-hand side is just waiting to be simplified with something on the left-hand side, right? So I got to see how this shakes out on the left in order to help me do, you know, work my magic on the right, right? Now I'm multiplying vectors, right? Even though it's a crunchy set of vectors, a vector difference, it's still the same idea. I have a binomial multiplied by a binomial, right? If I actually knew what the vectors were, as in, you know, instead of v, it was v1, v2, v3. And then v1, v2, v3 was a set of specific values like 1, 2, -7 or something like that. Then I could carry out operations, but I don't have that information, so I got to work with it in general terms. But I can fall back on my knowledge of algebra, right? So I'm going to multiply the v times the v. The problem is, just like before, v is a vector with v, right? When I dot them together, I'm looking at v dot v. I would not be able to carry out that multiplication without additional information, but fortunately we have additional information. But I'm going to write it out and then we'll clean it up. All right, so v dot v, poor quality v. Then my outers, get another highlighter involved here. So my outers, that's going to be v dot u, but negative. And then my inners are going to give me the same thing. All right. So my inners, same thing. So I'm going to have 2 of those. So minus, let me change it up, -2. And then v dot u or u dot v, it doesn't matter. The alphabetical order, I'll put u dot v first. I'll put u first, then the dot v. All right. Then 2 negatives multiply to a positive. So the last computation would be multiplying these 2 together. The u's, again, it's u dot u. So plus u dot u. Now, fortunately, like I said, we have rules. We just invented them, kind of. V dot v is the same as v squared, magnitude of v squared. All right, so that's great news, because what that tells me, and this is the grand finale here, the pièce de résistance. This is going to be magnitude of v squared. This is going to be magnitude of u squared. All right. I'm going to carry down all the other stuff, like literally all the other stuff, including the right-hand side. I might have to move some things. Smidge it over a little bit. Smidge it over a little bit more. All right. Now on both the left and the right-hand sides, I have a v squared, magnitude of v squared. Those will cancel. I got a magnitude of u squared. Those will cancel. All right. So on the left, I got -2 u dot v. On the right, I got this jimmity jammity here. Now you can see I have a common factor on both sides of -2. I can wipe those bad boys out. So what I get from this is a new relationship, a new way to think of the dot product between two vectors. U dot v is equal to the magnitude of u. I'm just using commutative property to change it around. I like the consistency there. You know, alphabetical order. Keeps things organized. Magnitude of u dot magnitude of v dot cosine of theta. All right. So that's a nice alternate definition of the dot product. All right. Magnitudes of two sides times the cosine of the included angle. All right, I'll talk about that deeper meaning in a second. All right. But then a consequence of this is if I were able to solve it for cosine of theta, which I will be able to, we now get the cosine of theta is equal to u dot v divided by the magnitudes multiplied. All right. Now there's an additional consequence. There's consequences to everything. You know, it's really kind of interesting and alarming at the same time, where it's like, oh, there's even more involved in this. This is crazy. This is getting out of hand. This dot product seems like it might be pretty important. But also, if you really think about it, it's not, based on what we did in the last couple of pages, it's not a difficult computation to come up with a dot product. But it sounds like we're getting extra meanings from this, right? And so that's what I intend to sound like, so that's good news. So cosine of theta, I'm going to write it as u over the magnitude of u times v over the magnitude of v. All right, what this is the unit vector in the direction of u. And the other one, I mean, I suppose you wouldn't have to write it because it's going to be the same thing. I'm just going to copy paste it. And I'll actually move it over a little bit. Change my arrows up. Unit vector in the direction of v. All right, so we're getting closer and closer to a truer understanding of what this dot product really means, aside from just hey, let me just multiply some things. You know, what's it really telling us? We're getting there. Hey, we're getting there. You know, and there are some applications of this that are going to come into play that are really kind of drive the point home. So a lot of good stuff coming. But still in skill mode, you know, aside from that awesome derivation there. There's different schools of thought when it comes to Calc 3, content-wise. I know a lot of people, you know, I don't know how many people have taken this course before. You know, maybe this is your second attempt, but I teach this class in a very particular way, right? And it's not always to the liking of everyone, but here's the thing: I don't care, right? And why the reason why I say that is because I play for the deep understanding, the underlying concepts. We can do the skills. Skills are easy. I'll take you through the skills in a minute. But if you want to really get something out of this content, we got to strive to understand not only the how, but also the why. All right. So, because I know that other teachers are going to be like, all right, the dot product, that's simple. You just do this, that, and that. And then let's move on to the cross product, which is simple. You just do that, that, and that. And before you know it, you're through the whole curriculum. And then you go and sit in a differential equations class. Well, maybe not differential equations class, but, you know, like an applied mathematics class. And you have no idea what anything means because you didn't get the good foundation in Calc 3. So I kind of felt the need to say that just because we did 2 proofs in a row, really. And there's got to be someone in the room that's like, how or why is this important, right? And so I figured if I didn't take an opportunity to address that here and now, you know, I wouldn't be doing my job, all right? But we're going to apply this. We're going to see even more about where it's useful, like what place it has in Calc, and why we need to know it to begin with. And then on top of that, we'll get into the geometric meaning behind all of this stuff, all right? Because, you know, we just got a little taste of it, law of cosines. All right, there's something to that, but let's just keep on keeping on and see where it takes us. All right, it's kind of like there's a plan to all this. So numbers 6 and 7 are asking us to find the angle between each pair of vectors. Now, personally, I never really liked the IJK notation, so I tend to go right into the component form. There are some situations where you have to use the IJK just to make your life a little less miserable when it comes to computations. But I don't like defaulting to IJK if I don't have a need to. All right, but I gotta get across the idea of becoming fluent between the 2 forms of notation. So you'll see the IJKs mixed in. Generally, the first step you're going to do is what I just did, convert it over into component form and then go from there. All right. Now, in each case, we need a magnitude. So I'm going to call the first one U and the second one V, just to make it coincide with my formulas, just make life a little bit easier. So if I want the magnitude of U, I'm dotting U against itself. I could also think of it as, again, just the sum of the squares under a radical, but, you know, that's fine too, you know, so, so there's an additional step, but I'll get to that in a second, right? Because we're going to pop a radical on this whole thing, but I'd look at it and say 1 plus 1 plus 1, which is 3, and then what I do is I retroactively go back and say boop, boop, and boop. All right, and all that came from the proof. You know, you could look at it and say, okay, well, that didn't really do anything. Like, why do we do it that way? I wanted to do it that way. I like doing it that way. Just like if you were to take the distance formula and apply it, I could say, why'd you do it that way? Your answer should be something like, that's the way I like to do it. And I say, okay, cool. I like my way, you like your way. Nothing wrong with that. All right. So then magnitude of V, again, v dot v. So 4 plus 1 plus 9, so 14. And then, like I said, I just like to go boop, boop, boop. It's kind of it's like back in the day when I would get recess detention for doing something inappropriate in school. And I'd have to write on the chalkboard 100 times, I will not do the thing that I did. Instead of writing the sentence, you know, one time, then again 100 times, I went word by word, right? So I 100 times, will, all the way down the line. That's just the way my brain works. So, you know, that's fine. You like to do it a different way, that's totally okay. Now, cosine theta, let me get another color here. I'm gonna go with this navy blue here for those keeping score at home. So cosine of theta is gonna be equal to the dotting of u and v. So that's gonna be 2 plus -1 plus -3. And that's gonna be over the product of rad 3 and rad 14. So we're looking at cosine of theta, 2 minus 1 is 1, so -2 over root 42. Then in order to find the value of cosine, I would just find, I'm sorry, the value of theta, I would just find the inverse cosine of both sides, which is super easy, barely an inconvenience. It's really up to you which way you want to go. Oh, I think I need this for stat. Oh, I can't remember what class this was. I know it's stat, I just can't remember if it's AP or not. Hold on one sec. Pause the video real quick. Resume recording. All right, so I hit that little wrench jammy there. I want to make sure that I'm in. Well, it doesn't matter what you're in. I just want to make sure I know what I'm in. You know, so if you want to go back radians or degrees, pick the one you want. It doesn't make a difference as long as you use the appropriate notation based off of the one that you're the mode that you're in. All right, so I'm going for the inverse cosine. I'll make the little note here. So this is going to be theta is equal to the inverse cosine, or arc, arc cosine. So function, trig, arc cosine, -2 divided by the root of 42. And I get my angle, roughly 108 degrees. Just be mindful of rounding instructions on an assessment, as you know. I'll just move this over a little bit. I don't need it that big. All right, so that's not too bad. You know, you got to do that little background work, but you know, it's basically trig, you know, college algebra trig kind of deal going on here. So hopefully that's something that doesn't intimidate you rather than being you know, a terrifying experience. All right. And hey, look at this. Great news. It didn't involve the unit circle for a change. That's a win, kind of. Unless you really studied the unit circle, in which case you're ready for any unit circle problem I can give you. That's a little bit of a different story. All right. At some point, you know what? I'll take this as a typo. It's not really a typo, but I need somebody to help me remember to do stuff. And so I'm gonna count that for bonus also. You know, like it'll count as a typo. I give unit circle bonus every unit. So you're going to, hopefully, if you'd like to take advantage of this bonus opportunity, send me a message saying, please remember, words to this effect, please remember to post the second unit circle bonus, all right? It's going to be just like the last one, except it's not limited to just sines and cosines around the circle. It'll have tangents in it, right? So I'm spicing it up a little bit. I made the first game I just found on that website, but the games that will be the bonus for the second and third unit, because I have another one for the third unit too. I made those myself, so it's a point of pride for me, you know. So I want to make sure everybody has an opportunity to tackle those. Right. So, and it looks like somebody's getting them in, which is good. Need all help I can get, folks. So the next one, same general idea. Designate one of them as U and the other as V if you want. If not, if you keep it straight, that's perfectly fine too. You're going to have to find the dot product between the two of them for the numerator. So I'm going to do this one a little bit more on the fly. We're going to have -4 plus -20 plus 24. Then on the bottom, we're going to have, you know, I'll call, like I said, you can designate them any way you want. I'll call one of them U and the other V. On the bottom, I need those magnitudes. Or, well, under normal circumstances, I would need those magnitudes. But as it turns out, my numerator is equal to 0. So the whole thing is equal to 0. All right? There's an exception to that relationship, and that is if the bottom's also equal to 0, then it's indeterminate. So you wouldn't be able to find the magnitude between two vectors. But in order for the denominator to be equal to 0, the magnitude of at least one of the vectors would have to be equal to 0, which means that one of the vectors doesn't really exist. So how do you find the angle between two vectors if one of them isn't really there, you know? So you can kind of rest assured that if you have two non-zero vectors and the dot product between the two of them is equal to 0, then the angle theta is going to be equal to 90 degrees. All right, cosine could be 90 or 270, but you could also think of 270. 270 one way is 90 the other. So if we're looking for the absolute value of the angle separating the two vectors, because it is in a geometric sense, we're only looking for positive values, we would be looking for an angle that could exist in a triangle. So I would want angles that are less than 180 degrees. Okay, so we get a 90-degree angle. And if you didn't know that, your calculator it'll definitely clue you in on it. See, it spits out that 90 right there. All right, just check your mode. Just make sure you're in the right mode. All right, because if you do it in radian, well, in radian, it'll just look different. It'll give you something equivalent to 90. Oh, it actually converted it for me. 1.57. If you don't happen to know off the top that that's equal to pi over 2, then you could be staring at it for a while. But yeah, when in doubt, put it in degree form. And if your answer calls for a radian answer, convert it over to radians later. You know, there's nothing wrong with that. That's one of the reasons why you learned how to convert between the two, right? So that leads us to a nice little consequence of dot products, and that is orthogonality, right? If the dot product between two vectors is equal to 0, then those vectors are orthogonal to one another, right? So that's pretty solid stuff right there. Okay. So when the example that follows, which is kind of a waste of an example because we already got one that shows orthogonality, number 7. So I would say, therefore, U and V are orthogonal. But if a question's just simply asking you, hey, in the previous one, it just said find the angle. Here it's asking you whether it's orthogonal. It's really just asking for you like a binary answer, like yes or no. So what I would just do is simply find P dot Q, 10 plus 0 plus negative 10, result is 0, therefore P and Q are orthogonal. Which is pretty awesome. It's a nice, easy question. You could expect an orthogonality question on the test. I'd like to think that well, not everybody agrees. So in my mind, what I try to do on a test is I balance out like the disastrously challenging question with something that's pretty much a gimme, right? So like it's in the eye of the beholder, but on the last test, you might have thought, for example, the physics question, the one with the boat being pulled with the two forces. Maybe you thought that was the hardest one, but then that was balanced out by the proof that all you had to do is go in your notes and just copy it down. So, like it should be like that. So this will be the balance to something that's more challenging on the test, and I count them all the same in terms of values. So I look at it and say, okay, well, I'll give you the free 5 points for this simple question. And then I'll, you got to tackle a much more challenging question, but it's still the same 5 points, right? So I try to do little things like that so that it's, I call it being unfair, but in your favor. That's how I like to make my tests. Unfair, but in the favor of students. Right? So again, whether you agree or disagree is a different story. And sometimes best laid plans, I go into a test thinking, okay, I'm sure this will be a nice, easy question for everyone. And it doesn't play out that way, but that's my mindset always going in. I was just buying myself time. Well, that was necessary information, but I was also buying myself time in case anybody was still copying. The examples on the next page are asking you to find the measure of the angles formed by each pair of vectors. Just knowing that I is the vector 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. I'll just jot that down on the top. This should be pretty easy, right? Because it's really just doing more of what we just did. So I, 1, 0, 0, J, 0, 1, 0, and K, 0, 0, 1. All right. So 8, 9, and 10 are all just more of the same kind of stuff. So what I'll do is I'll just put stars on those problems so you could tackle those on your own, and we'll make sure to go over them to next class, almost at tomorrow, next class. All right, but I'd like you to have an opportunity to take a look at them first. But we're going to move on to something called a projection. All right, so we have components and we have projections. The notation is really kind of weird. I mean, it's more than kind of weird. It's extraordinarily weird. All right, but I'll get you through it. In terms of just kind of building out that definition. Vector projection of V onto U is the vector labeled proj or projection sub U of V, right? So in terms of the notation, it's what the subscript is the vector that you're projecting onto, right? So more on that in a few minutes. It has the same initial point as U and V in the same direction as U and represents the component of V that acts in the direction of U, right? If theta represents the angle between U and V, then by properties of triangles, so basically by knowledge of math, we know that the length of the projection of V upon U is, that magnitude is equal to V times the cosine of theta, which I'll walk you through in a minute. When expressing cosine in terms of the dot product, this becomes, and there's like more of a proof, but like I said, I'll take you through the origin story behind that. But before I do that, You just want to give you like a little simple explanation of what the hell all that means, right? So you look at it like you got two people, you know, like that question on the test. You got two ropes and you're pulling the boat in with the two ropes, right? So, or I like this one too. Two people carrying a couch up a flight of stairs. For all you Marvel fans, you have Tony Stark and Rhodey trying to pick up Thor's hammer in Age of Ultron, right? So all of those are cases where you have two forces acting upon an object. So the idea is that whatever I'm contributing to the action will impact the amount of contribution that my partner needs to apply, right? So if I put in 100 pounds of force, so I'm really pulling hard, that's less force for the other person to have to put in, right? Now the couch analogy is a little trickier because, you know, like I could put in like 200 pounds of force. And so, you know, if my partner isn't putting in that kind of force, it's not going to be balanced. There's more to it than that. But if Tony Stark is pulling the hammer with 500 pounds of force, and Rhodey is pulling the hammer with 700 pounds of force, you know, depending on how they're pulling it, they may not be getting a combined 1,200 pounds of force in the positive direction, right? If they're pulling away from it, they might only be getting 1,000 pounds of total resultant force, right? But the question when we're dealing with projections is how much of the force that Tony is applying is being redirected in the direction of Rhodey, and how much force that Rhodey is applying is being projected onto Tony's pull, all right? So that's really it. Same thing with the boat idea. If me and another person are pulling, you know, two different ropes, if I pull it really hard and that person's kind of pulling it, and I'm like, hey, are you pulling it? Are you even pulling it all? They may be like, well, I'm pulling a little, but you're pulling so hard that I didn't really have to put in a lot of work, you know? So the amount of work that they have to apply is nowhere near as much as it would be if I wasn't, you know, producing the lion's share of the force, all right? So that's what the concept of a projection is really talking about. You know, how much of the magnitude of one vector is acting in the direction of another, all right? So here I'm looking at, and I'll just bring right in, we'll just take a look at the picture. We have two vectors, vector v and vector u. Now vector u is that whole shebang at the bottom, right? It's overlaid with the projection of v upon u, right? That orange, I think it's orange, like rust color arrow, is the vector projection of v upon u. All right. So that's the amount or the magnitude of, we could say force for lack of a better term, that v is applying that is in the direction of u. All right. So what we're going to do is we're going to figure out what that means algebraically, because regardless of how long that line is, I'm always going to be able to drop an altitude. So that line at v, I'm always going to be able to drop an altitude. All right. That altitude is going to form a right angle with the other vector. All right. And then whatever that line segment is that starts at the intersection point and meets at that base of the triangle at that right angle. So this distance here, that line segment will be, by definition, the vector projection of v upon u, right? So I'll just show you another quick one, and we'll get into the algebra of it in a second. I just want to drive this point home. I got a couple of black markers here. I don't like that, right? So let's say v wasn't doing really any work whatsoever, and u was doing a ton of work. All right, so I got v over here, hardly doing anything, lazy V. And I got you over here, a real go-getter, right? If I wanted to know what V's contribution to the overall movement was, and you got to imagine instead of pulling the rope, you got to imagine V is probably on, you know, one hand looking at his phone or her phone, and the other one is like, I guess I'll pull a little bit, and that's really all you're getting, right? U is getting very, very upset at V here, right? So what we would do is drop an altitude. This little line segment here, which I'll do in purple, that little guy, that little teensy tiny bit, that little smidge of nothing, that is the projection of V upon U. All right, just that little guy. So it all depends. It all depends on what each one is contributing. All right. So what do we get from this? Well, we get another proof. That's what we get. So here's theta. V has a magnitude of some unknown value. I'm going to bring it in a little bit. All right. That orangey looking one, that's also going to have a magnitude. It's the magnitude of whatever the projection of V upon U is. And then we also have the magnitude of U, but that's kind of beyond what we're looking at here, right? So what we can get from this is the idea, just based off of simple right triangle trig, that the cosine, because I have the adjacent side here, this is adjacent, and this is my hypotenuse. Cosine of theta is going to be equal to the projection, the magnitude of the projection of V upon U over the hypotenuse, which is the magnitude of V. Ah, what just happened? Sorry, coming back. I slipped. All right, so we get that relationship, and then you look right above it, and you say, oh, that's where it came from. It's the same thing, except I cross-multiplied, right? So we're looking at this guy here becoming that rule, right? So then the big question is, all right, well, what does that mean? You know, like, what does that get us? Now, before we get to that, what we do is we define a new relationship. So the component of V acting in the direction of U, that is defined as the magnitude of the projection of V upon U, right? So that, it's like, okay, well, now we're just making up a new term. It's a little annoying. I don't like it. I don't like making up the new term, because magnitude of the projection, that works beautifully. That's perfectly fine. But to understand the language of this stuff, you got to kind of get involved in it, right? So what we're doing is we're creating a new vocabulary term, and that is, and I'll just kind of box them. These two things are one and the same. They mean the same thing, all right? Now, the projection of V upon U, we just discovered that that's equivalent to the magnitude of V times the cosine of theta. And earlier, we discovered that cosine of theta, based off of that alternate definition of the dot product, is equal to this whole shabiggity bangity boom here. All right, so if I want the component form, or not component form, the component of V acting in the direction of U, all right, so when I say component in this context, because we're overusing the term component now, it's frustrating, all right? But if I say the component in this context, I mean the part of vector V that's helping out U, all right? By a little simplifying, all I would end up having to do is find the dot product of U and V and divide it by the magnitude of U, all right? So that's, I mean, as far as things go in terms of a proof, that's pretty not bad, right? But yeah, just to kind of get at the origin story here, that's pretty important stuff. Now, you could also think of it as, okay, here's another concept. Is this going to be useful? When are we ever going to need this? I think it's pretty important to know what the contribution of one vector is in the direction of another, right? So, because those vectors could be lots of things. You know, if you're thinking about economics, if you're thinking about thermodynamics, if you're thinking about kinematics, like any application of mathematics that you can think of, this concept is in play, right? So if I look at it, it's just like energy usage, right? So the overall vector would be my electric bill. If I want to keep it domestic, you know, keep it simple, I could say, all right, well, I got air conditioners going, I got the TV, I got the fridge, I got microwaves, I got an air fryer. I'm constantly charging the Sonicare toothbrushes. My electric is also being or it's contributing towards charging devices, Wi-Fi, you know, all these different things. If I want to know what contribution one of those types of device or devices is or the impact it's having on my overall energy expenditures, then this concept would come into play, right? So it's pretty interesting, right? And also, you know, temperature. So like you think about it, you know, you got to in your own homes, you have fans, maybe you have air conditioners, but then you take a hot shower, right? So you have a bunch of things going. Maybe someone's cooking in the kitchen, so you have heat sources and you have sources, you know, like where cooling sources, and so the overall contribution that or interactions that they're having with one another. I mean, don't get me wrong, though that's really complicated computations, but it all starts with this concept, right? So pretty challenging and important stuff, because what ends up happening is once you, so I don't know how many of you are going into the sciences, how many of you are focusing on pure math, and how many of you are like, I just needed this for my major and I want to be done. So everybody's kind of doing it for different reasons, but I know from experience, because I've taught the class and I took the class, that once you finish learning all the individual branches of mathematics, then it's time to start combining them, right? So when you get into, like I took an applied mathematics course, or actually several of them, and it drew on everything that we had learned from different math classes. And so one thing that we talked about was energy consumption, and it involved not only vector operations, but also probabilities in terms of vectors, linear algebra and stuff like that, all coming together. Is really beautiful, but also very challenging, right? So we're still in foundational territory, but there's definitely applications of this stuff beyond, you know, your ordinary textbooky kind of stuff, all right? So on the next page, the component of U on V, written as component of U on V, it's a scalar value, right? So that's all the stuff I was saying. Now, if we want to actually find the projection of V upon U, and you're given a component value, so you actually know the magnitude of that projection, then all you'd have to do is multiply it by the unit vector in the direction of U, right? So that part shouldn't be too bad. But the good thing about it is, if you needed to actually find the projection of V upon U, by doing all of these machinations behind the scenes, machinations, I don't know what the right word is, we derive a formula that's much simpler to use, all right? So if I need to find the projection of V upon U, I would just go right for this guy. But that's if you're sourcing a formula. If you're just looking at it like, wait a minute, I'm just taking the component value or the magnitude of the projection and multiplying by a unit vector, why don't I just do that? You know, that's that's what I'm hoping for. You know, that's really what I would like you to kind of walk away with in terms of general understanding. But but I'm not going to begrudge you using a shortcut formula either, you know. So the examples: find the projection of V on onto U or upon U. So I need the dot product. I need unit. I need magnitudes, and I need I just need U. So it's not going to be too bad, because I need just to crank out a couple of dot products, and I'll be good to go. So U dot V, and then I'll do U dot U to get me the U squared. Right? Again, personal preference. So U dot V, we got -3 plus 20 plus 3. U dot U, 1 plus 16. 1 plus 16 plus 9. All right. And again, that the U dot U, that's the one that I retroactively go back with the radicals. Right. So that's going to be 26. But because I'm looking for, because this is really giving me, oh, actually, I need magnitude squared anyway. So this time I don't actually have to do that. That's great. All right. So this is equivalent to magnitude of U squared. You know, sometimes you got to make the adjustment. This is just one of those times where you don't. What do you know? I'm just cleaning it up now. Make it to look a little nicer. Disgusting plus sign. All right, so yeah, I'm going to get that 26. I'm looking at just a clean 20. All right, the quotient of those two values is going to be that first part of the fraction, right? So I can just do a quick, you know what? I was going to do it over the whole thing, but let me just do it one piece at a time. Oh man, it used to lock into just a straight up horizontal line segment. Now it's just so wonky, I don't like it. 10 over 13. Nice reduced form. And then we just multiply that by U. And what we get is the projection. We're looking for V upon U. Yeah, V upon U. Brain cramp there for a second. 10 over 13, -1 for 3. Now, this is a scalar multiple. If I'm actually looking for the vector itself, as annoying as it might seem, we do want to go through and distribute. All right, so -10/13, 40/13, and 30/13. Okay. So it's not really that crazy. This takes a little doing. Pop a little star on number 12. I wanted to tackle the word problem, though. A good-looking word problem always finds its way onto an assessment, so definitely worth spending the time. Container ship leaves port traveling 15 degrees north of east. Its engine generates a speed of 20 knots along that path. In addition, the ocean current moves the ship northeast at a speed of 2 knots. So it should sound pretty familiar. I mean, this is kind of like what we did in the last unit, except we're going to use a projection approach on this. And really, I mean, I've been meaning to do this. Definitely not tonight, but maybe next time what I'll do is I'll show you how, with a simple few adjustments, the formulas that we use for this technique can be manipulated to be equivalent to the formulas that we use in the other technique, you know, for vector sums. Anyway, considering both engine and the current, how fast is the ship moving in the direction of 15 degrees north of east? Round your answer to 2 decimal places. So 15 degrees north of due east is, and I'll just kind of highlight it here. It's that bad boy right there. What I want to do is figure out what W is contributing to the vector motion in the direction of V, right? So this goes back to that diagram I was talking about 2 pages ago, maybe last page, I forget. Drop in altitude. It's a 45-degree angle in here. Oh, sorry, 30-degree angle. The whole thing is 45. The triangle itself is going to have a 30-degree measure of separation. So it's 30, 60, 90 right triangle. That's useful information. What I'm trying to do is figure out how fast the ship is moving, so we'll know information related to the current, we'll know information related to the boat, and then put it all together, we get overall the movement of the boat in general. All right. So I'm going to use purple. Draw a little arrow here. That arrow represents the, well, I'll write it as the magnitude because that's really what we care about. Magnitude of the projection of W upon V. All right, so instead of V upon U, it's W upon V. Right, so that's a little bit of an adjustment, but not an unmanageable one. Right. If you compare it to the formulas, and I'll just kind of bring it back, you know, just look at the part of the formula that's related to the sorry, the magnitude of the projection. I could just kind of bring it in a little bit, highlight for you. It would be this guy here. It's the dot product between two vectors, but then you're dividing by the magnitude along the path that you're following, right? It's the dot product divided by the magnitude along the path that you're following. So that's pretty straightforward, you know. So so that's what we'll do here. You know, you could jot it down too, you know, just kind of do a little substitution. The projection upon V of W, we're looking at W dot V over the magnitude of V. And just kind of chuck it in there, just have it ready to rock and roll. All right. Again, we got the angles, so we'll take care of that in a minute. The ocean current moves at a speed of 2 knots. So I know that the magnitude of W is 2. And we also know that the engine generates a speed of 20 knots. All right. So without the current impacting the speed of the boat, it would move to 20 knots, but the current is going to impact it. But I can say that vector V ought to be 20. So we have that information. The issue is we don't have anything in terms of a dot product between V and W and V, V and W. Right. So at first glance, it seems like, oh man, what are we gonna do? We got a problem here. But if you think back, you know, we can look here. I can kind of steal it out for you, but you could also just kind of go back to the work we did 2 pages ago, which is the alternate rule for the dot product, this guy. U dot V is the same as the magnitudes multiplied by the cosine. All right. So this guy over here, we're going to look at this as the magnitude of W times the magnitude of V times the cosine in between them. I'll just leave it as theta for now. All right. So with the substitutions and cancellations and such, we actually get something a lot simpler. You'd be looking at magnitude of W cosine of theta. So magnitude of W is 2 cosine of 30 degrees. So 2 times radical 3 over 2 is radical 3. All right, so radical 3 knots is what W is contributing in the direction of V. Right, so we're talking about 1.7-ish knots. All right, so about 1.7 knots on top of the V. All right, so if I want to know what the boat is actually doing in terms of speed, I would take the sum of that value and the 20. Right, so the speed of the boat is 20 plus radical 3 knots. All right, and in decimal form if we want, I guess. Round to the answer to the nearest 2 decimal places. So there's that, 20 plus the square root of 3. So about 21.73 knots. All right, so that's the contribution that the current is offering. The 1.73 combined with the 20 gives us the total total velocity. All right. So it's it's a simplistic application question, but it starts kind of getting the ideas going. It gets the juices flowing a little bit. Hopefully, that's the idea anyhow. All right. So again, use my simplistic concepts and my simplistic examples, and jazz them up with your own flair. Just had a brilliant idea that I'll talk to you about next class once I've had an opportunity to think it through. Yeah, it'll be great. Freaking sore throat is killing me. So, hopefully not. Knock on wood. Jesus, Christmas. So we're going to talk about the cross product now. We'll just get into the skill, and then we'll bring it all together. We'll talk about cross product and dot product together, and we'll get the true meaning behind both of them. All right. The cross product actually has as its basis the dot product, right? The cross product comes from the dot product, right? So we have dot product multiplication of 2 vectors that results in a scalar. Cross product of 2 vectors generates a third vector orthogonal to the first 2, right? So what I'll do is I'll just kind of get you started with the proof and then go from there. They're really, I don't want to get too much into the proof itself because it's like a full page of algebra, and it's not pretty, and it's kind of like a class period in and of itself, or a class session in and of itself. So what I'll do is I'll just kind of get you started with it so you get an idea, and then I'll get into the skills behind it. All right, so we have U and V are 2 non-zero vectors. What we're going to get is a vector W that's orthogonal to both of them. So what I'll do is I'll draw 2 arbitrary vectors U and V. Now, those 2 vectors, I have them, I'm trying to do kind of a perspective drawing. Those 2 vectors are living in their own plane, but in my mind, I have it as that they're kind of like on the XY plane when you're dealing with the ordinary XYZ axes. All right. So what's happening is you're going to have an offshoot here of a third vector that's going to be orthogonal to both of them. So it's going to form a right angle with both of those other vectors. So now this is the part where it gets a little kooky in terms of the diagram. I'm going to have this vector forms a right angle. All right, that's W. But I'm also going to have this vector V that forms a right angle. Kind of took off on me there. So we have two of them. Now, it's kind of weird, but what that means is that you're dealing with a vector W that will actually be orthogonal to an entire plane. All right, so I just kind of look at it like you got a sheet of paper. All right, I don't know how well you can see this, but you got a sheet of paper, and the corners, or the two edges that make the corner, those form two vectors, and the sheet of paper is a plane. All you're getting here is a third vector that's orthogonal to that plane. All right, so it's orthogonal to the one side, it's orthogonal to the other side, but then in turn, it must be orthogonal to the span of the plane. Every point on the plane, if I were to take a parallel vector to this one, to the one that is the cross product, any vector that is parallel to that would necessarily have to be orthogonal to the plane itself. All right, so that's one of the applications of this, is that we're going to learn, based off of the cross product, how to define the equation of a plane. Right? It's pretty important stuff. But at this point, all it really means is that the dot product of U and W, that's not a U or a W, U dot W is going to be equal to 0, and the dot product of V and W will be equal to 0. All right. Now, we could get into substitutions and things like that, but if we do that, then we're actually going to be doing the proof. But what I'll do is I'll just kind of give you the beginnings of it. All right. So we'd be looking at do a little color coding here. We have U, which is U1, U2, U3. That's going to be dotted against W1, W2, W3. With the result equal to 0. Then I'm just going to do the same thing, just with V's. And let me do the coloring. Now, when you actually apply the dot product, you get that gloriously messy algebraic set of equations that form a system that you would then have to solve. All right, so I'll take you through the next step, but then that's where I'll stop, because it does get out of hand pretty quickly. You'd have U1, W1 plus U2, W2 plus U3, W3 is equal to 0. And then you'd have V1, W1 plus V2, W2 plus V3, W3 also equal to 0. And then you'd use a systems of equations technique to eliminate a variable, right? So you'd multiply the first equation by, let's say, V1. and the second equation by u1. That'll cancel out the first variable, and then you're off to the races. All right, so the idea here is that you would then solve the system for W in terms of U and V. All right, and then what that would get you would be a really hideous set of vectors, a set of components for a vector that end up being this, what I'm highlighting there. All right, so from those two equations and proper algebraic technique, you would end up with those components, which in turn would be your cross product. All right, so I know I have a video online that walks you through it, but it's a little choppy and it's overly lengthy, and I think I go on like 5 tangents throughout it. So I'll take this as a typo. Just a reminder, make a fresh new video for a cross product derivation. All right, so yeah, I'm just giving bonus points for reminders. That's all I need. Because I forget stuff. As the older I get, you know, I was forgetful to begin with. So throw age into the mix, it's all over. So we can find the cross product using that lovely looking formula, or we can use what's known as the determinant shortcut for cross product. There's a couple of reasons why you would want to use a determinant shortcut. One reason would be a pretty simple one. It's a whole lot easier. All right, just keep it simple. Another reason would be along the same lines is your calculator will do it for you. All right, whether it's Desmos or a graphing calculator, or a TI graphing calculator, it will, either of those calculators will find a determinant for you, right? But I'll talk more about that next class. What I want to do now is just take you through the process once, maybe twice, of figuring it out by hand, and then go from there. All right, so what you do is when you're given your two vectors, U1, 2, 3, and V1, 2, 3, we create a matrix, a 3x3 matrix that consists of a row IJK, which I'll talk more about next class, because what that actually implies is that you have a vector that contains another vector. All right, so a vector within a vector. There's a strange underlying meaning to that I need to dive into also. All right, but that's your initial setup. So when we're talking about P cross Q, that's not a P. What I do is I'm looking for the determinant. Determinant is talking about really the value of a matrix, but it's even deeper than that. The determinant's actually giving you, depending on the system that you're in, if it's a two-dimensional system, it's giving you the area of, well, the magnitude of the cross product would give you the area bounded by the vector if you were to create a parallelogram, right? So it's pretty useful stuff, right? So cross product's actually a nice nifty way for area. In 3 dimensions, it helps you find volume, and at 3 dimensions and beyond, helps you find volume, right? So I'm indicating IJK here. We have the -1, 2, and 5. And we have 4, 0, -3. Okay. So the 1, 2, and 5, the 4, 0, -3, each one gets its own row. So then if you take a look at the model here, you see we have a matrix followed by I minus another matrix followed by J plus another matrix followed by K. right? So that's what we want to have. Black. All right, so I'm just creating the structure. These actually look pretty terrible, so I'm going to use the line draw tool to fix them all. Sorry. A little waste of time, but all right. So then the question becomes, all right, well, what values go in there? Well, you look at the model, you see we have a U2, U3, followed by V2, V3, right? So I don't want to get too far into linear algebra because I have confused the living daylights out of people in the past when I've done that. And I don't want to confuse the living daylights out of people anymore. It's like my New Year's resolution. So what I'm going to say is there is a linear algebra justification for why I'm allowed to do what I'm about to do. All right. And as long as you believe me on that, we're not going to have a problem. All right. So what we do to come up with our first matrix is we look at the letter I. And what we do is we eliminate, I'm going to temporarily eliminate, but I'll erase it in a sec. You eliminate the row and the column that I is in. You know, don't do it permanently because we still need those values for J and for K. But whatever's left over is what is going to make up the matrix for I. All right. So again, you look at I. You say, okay, well, why do I know I? Well, here's I. Okay, so I look at I and I say, all right, I is in this column and this row, right? So I'm crossing all that information out and I'm just taking note of whatever remains. So 2, oops, a little thick, 2, 5, 0, -3. And that's it, right? I mean, we got to compute what the determinant is there in a minute, but that's a different story. We just want the numbers at this point, right? So it's the same idea for J. What you do is you take note of where J is. You wipe out the row that J's in and the column that J's in and take note of everything else, all right? So the 2 and the 0 are gone. The only values that remain are -1, 5, 4, and -3. And then the last computation, or last, it's not even a computation yet, the last part of the algorithm here is to take note of where K is. Eliminate the row and column that K is in. So you can see in each case, we're always eliminating the top row. That's really, at this point, it's really just a set of placeholders for us. But in doing so, it allows us to eliminate the column of entries corresponding to K. And here we see that we're left with just a -1, 2, 4, and 0. So now we got this information, we got to find the determinant for each value, or for each letter, I, J, and K. So there's 2 ways to do it. If it's a 2x2 square matrix, very easy to do by hand. It actually takes longer to type the information into your calculator than it does to compute it by hand, assuming the numbers are reasonably friendly. Right? What you do is you multiply down the main diagonal. So I take my 2, multiply it by -3. So I get a -6. And subtract from that the product up the other diagonal. All right, main diagonal starts on the upper left and goes to the bottom right. The other diagonal, the only two remaining values are 0 and 5. So multiply those values. The result is always subtraction. -6 minus 0, -6. So I have -6i. Okay, so again, multiply down the main diagonal. So I got a positive 3 minus, then multiply up the other diagonal. So -20. And I get a -17, but you got to be careful. So I have a -17j. There was a plus a minus sign that was built into the function or the expression. So that has to come along for the ride. So I pop in another minus here. Take care of that in a minute. All right. Same idea with the other one. I got a plus sign that's going to come along for the ride. But I'm doing the diagonal down the main multiplication down the main diagonal. So that gives me a 0 minus multiplication up the other diagonal, 8. So -8. All right, so I got a plus here. I got a -8k. And this ends up being one of those necessary evils where it's like, okay, I guess we'll use the IJK notation because it's a little bit more convenient. All right, so this is equal to, so P cross Q is equal to -6i plus 17j minus 8k. And you could put it in component form if you want, but once you have it, you have it. So it's up to you at that point. All right. And so on the next page, it's just a couple of examples, or just one example, I think. And so that's where I'm going to leave you tonight. All right. So I'll come back to this page in a second. You're still copying, like 1 sec. What I'll do is I'll just put a star on number 2, and I'll ask you to tackle that for homework. The properties, you should have a look at them, but you don't have to worry about using property. You don't have to worry about those examples yet. I want to take you through those as a group. All right. So just number 2 on page 32 is where we're gonna leave it. All right. So you'll try this for homework. You know, you got a lot of stuff going on between the dot product and the cross product. So we want to make sure that we have an opportunity to get the skills down before I start getting into more of the applications. All right. So let me stop the recording.